Our next speaker this morning, Adam Thomas, who's come all the way down from Warwick. And I've absolutely forgotten your title, Adam. I apologise.
That's it. I wrote it on the board.
Oh, brilliant. When is complete reducibility inherited?
Thank you very much. Very much to the organisers for inviting me for the month and giving me this chance as we go, so I can forget about giving a talk very soon. So in short, the answer is sometimes. Okay, that's the 1 minute version of the talk done. But obviously, I didn't plan quite that stupidly. So what I want to do today is, well, explain what I mean by complete reducibility in what setting, and also what I mean by inherited, even though I guess that at least has some definition in terms of the English of the word. And so I thought I would start with some motivation. So it's a reasonable place to start. And it's not my motivation, so that's good. It's actually motivation of Sarah. So K is just any old field of some positive characteristic. And you let V1 up to VR be semi-simple, reducible, whatever your favorite term is, collection of representations of any group G. And I gave this talk before somebody asked what I meant by group G, which really did freak me out as a question. But I really do just mean a group. Then if the following is true, and you sum the dimensions of the vector spaces, one subtracted. If you do not reach P, then the tensor product, I guess really same model, right? And the corresponding tensor product is again semi-simple. And this is a positive characteristic version of a result of Chevrolet from characteristic 0, and it's sort of one direction of, if I give you some modules that are semi-simple, what can I say about the tensor product? And there's plenty of other results in this paper, but let me just say one more. So if V is semi-simple, already going to shorten that, and the dimension of V is no more than P plus 3 over 2, then the wedge square of V is semi-simple. So okay, so nice general results.
Yes. I'm sure you meant to write it on the board, but these V's are over K, right?
Oh yes, nobody. There will only ever be one field. I do not deal with cross. There's no. Yes, there's only one field. Yes. So this isn't the motivation to my question quite, in a way. It's a next paper of Sarah where he asked the question of, well, what happens if you want to go back? Can't remember. So what if I tell you that I had some tensor product of things that was semi-simple? What do I need to know that the factors had to be semi-simple? And so I think the paper is called something like converse theorems, which I think probably is also an overused term in mathematics, as most other words now are. So we proved that if V tensor W is semi-simple, then V is semi-simple if the dimension of W is not 0 or P. The M tensor product of a single module V is semi-simple actually does imply V is semi-simple. I don't need any conditions, any congruence conditions at all. And the wedge square of V is semi-simple, again implies V is semi-simple if the dimension of V is not 2 on P. And a combination of Serre and an appendix by Veit tell you that you can't do better than any of these if you're talking about still any old group. So they give finite groups, often some product of cyclic groups of order 2 and things that tell you you can't do any better than these congruence conditions. Okay, so the proof of this, and just generally the kind of question, when does something being semi-simple kind of pass to tensor products or the wedge square or vice versa, I believe is exactly what inspired Sayre to define this notion of complete reducibility. So I'm pretty sure he says that, I'm not just guessing. I've been trying to read his mind or something. So for me, my algebraic groups are, I'm going to say simpler. That's maybe not a good use of word either. But I just want a reductive connected algebraic group, and for the whole talk, I will have an algebraic closed field. It's not necessary, but most of the things I will define, and people who I'll be talking about later have generalized the definition to remove connected and talk about things over a non-algebraic closed field. But the questions I've been most interested in are already difficult for this guy, so we'll stick to that one. So a subgroup X in G is GCR, G completely reducible, but I've written it once on the board and that'd be it. If whenever X contained in P parabolic, mentioned this moment, then X is contained in a subgroup of P. And as a special case that I might need later, so I'll just mention, so the subgroup X if this is really easy to satisfy, i.e. you're never contained in a proper parabolic. Then never contained in group G. Okay, so usually I've been working on something to do with things like complete reducibility since I was a baby. So usually when I give this talk, I spend a long time worrying about exactly trying to tell everybody what a parabolic is and what a Levy subgroup is and exactly why this equates. But then I realized that, again, like with many things, I mean, they're telling you something you know, or you're not really understanding what I'm saying. So today, I thought I would try to just stick to the story I like, and so we're going to do a minimal amount of things. So if you're not happy with reductive connected algebraic groups over an algebraic closed field, then it's perfectly fine to just think of GLN. Okay, and the definition of complete reducibility and irreducibility are really easy. If I just write this as GLV, then it means nothing more than V restricted to X is completely reducible, semi-simple. That's why I often write semi-simple when just talking about modules, because of this being more of a subgroup structure condition. And X is G-reducible precisely means that V restricted to X is irreducible. And then why has it got something to do with parabolics and levies? Well, in GLV, parabolic is a stabilizer of a chain of subspaces, a flag, and a levy is when you stabilize, your levy is a stabilizer of a flag and a complementary flag. And so I can draw pictures. So that's parabolic, and a levy is, well, so I can put the identity on the squares and put stars up here, that's my unipotent radical, and then my levy is the bit on the blocks. And hopefully that sort of looks like the sort of thing that if I live in here, I'm completely reducible, but just living in here with stuff up here, I'm not. And irreducible meaning I can't ever put myself in a proper one of these staircases, so I don't stabilize any subspace. Okay, but that's got seemingly nothing to do immediately with what I was talking about over there, where I just seem to have plucked out Sarah to try and motivate the entirety of my talk. Again, so that's not true. So why is this related to that? And his questions. So, well, if X is an algebraic group, connected, reductive, semi-simple, all nice adjectives, with a faithful module V. So here's the sort of example of where the connection. So if I tell you the wedge square of V is semi-simple, so I'm trying to deduce something about V hopefully is semi-simple, then X is SL wedge squared of V completely reducible. So I said for GLN, you just think of complete reducibility and irreducibility as what you would on the module, and the same is true for SL. If you're in one of the other classical groups, it's ever so slightly different, and in the exceptional groups, there's not really a V which makes sense, which is why do it this way, you get some group theory notion from representation theory 1. So if the wedge square of V is semi-simple, then X is SL wedge square of V CR. Call that one G. And then if you let H, G is irritating in the way. That's the image of SLV into SL wedge square of V. Then V being semi-simple, is if and only if X is HCR. And so, says converse theorem, says we want to know that being GCR should imply that we're HCR for some subgroup. And here, so I have X sitting inside H, sitting inside G. This one says LV. This one. And so then X is GCR. And say I was interested in is X still H still. So that's the sort of inherited we're going to be talking about. And that's sort of not the only, like, just that which allows Sam to do this. All sorts of theory of saturation and other things, but that's kind of the motivation that I want to talk about these types of theorems, but when I take a representation or a module for an algebraic group and see if we can actually do a little bit better, and just in general, given that definition, which, as I said, I'm giving you a full kind of motivation, but it turned out to be very nice, and already people have been working on it before it was defined, which I always think is a nice way to know it's a good definition. That something like, if somebody gives you a subgroup and tells you it's GCR, is it still HCR, seems to be a very fundamental question. So, because I didn't do so much about that, let me at least tell you a bit, some more things about being GCR. Because right now it just looks like I've taken a representation theory definition and done, just turned it into subgroups for maybe no reason. So a quick sort of allude on reducibility. Okay. So first of all, it's nothing new in characteristic zero. It is just a renaming of the word reductive. Thanks to the semi-simplicity of modules in characteristic zero. Now obviously it would be pretty ridiculous if the same was true of positive characteristic. Why would we be bothering? So one implication is true. If you are GCR and you are reductive, and that's essentially nothing more than the Borel-Titz theorem. Okay, the reverse implication is not in general true. However, it can be. Maybe the answer to every question you sort of think is a indecisive one in this talk. Maybe, or sometimes. What about the reverse implication? Well, a theorem which is in a paper of Sayre, but as I said, these people had worked on it before the definition and essentially had done all of the work, other than a little case for G2. Too big find a little one. Cool. So if your characteristic is big enough, which is something that we like in algebraic groups, that if your characteristic is big enough, you should be back in the characteristic zero case, then the left implication is true for connected subgroups. So if you want something, as I'm concerned, interesting to happen, i.e. you get some subgroups that are not completely reducible, then P needs to be less than or equal to the rank. So a couple more nice things about complete reducibility. So these three people will be here in weeks 3 and 4-ish. And they did lots of work on complete reducibility. So let me just give you a couple of their nice theorems. So normal subgroups of GCR subgroups are GCR. I guess that's a nice kind of inheritance property. And centralizers, normalizers, of GCR subgroups are GCR. And there are lots more. And so what I want to focus on today is this question about, well, both ways. If I tell you I have a subgroup and it's GCR, when can I, and I know it lives in some H, when do I get to determine that it's still HCR, but vice versa? If I give you something in H that's HCR, does it always have to be GCR? So, gave those a name. The name wasn't unilaterally popular. So Alistair, I will get to some joint work with people, but in particular, Alistair, myself and David Stewart have a survey paper in the group St Andrews from 2023, where we give this definition I'm going to give, but then BMR wrote a book on complete reducibility after us. But Mike said he didn't really like the name, so he just changed it. But I don't like that, so I'm going to keep the one that I got in the literature first. So tough. Well, I was about to say, I do understand his objection to the name as well. Just don't really like theirs any better. So a subgroup H in G is descending hereditary. Also learned in giving the first talk of this, I'm very good at misspelling hereditary. So I really should have picked a different name. If for all connected subgroups, X and H, we have that X is GCR implies X is HCR. So we want complete reducibility to go down, which is probably what I'll actually refer to for the rest of the talk, but I don't think you can say downness and upness in a respectable academic paper. You can guess the rest. So ascending hereditary dot X is HCR implies X is GCR. And of course, you remove the adjectives and just call it hereditary if you can do both. So X is HCR and only X is GCR. Okay, and like what I was saying about how complete reducibility had been studied by people before Sarah gave it a name. This has been studied by people before people gave it a name. So maybe look at some examples and non-examples. Okay, so in the original paper, Sarah showed that Levy subgroups are hereditary. Hereditary.
Are you sure you want to stick with the word hereditary?
All right, I'll get tested for dyslexia one day and I'll have an excuse. Okay, so I will shorten Bate, Martin, and Rilla to BMR, because I'll say their names too often. So they then generalize this to say that centralizers of groups consisting of semi-simple elements are hereditary. So G can take F4 and E6. It's not a Levy, but it's a centralizer of a graph automorphism, which is going to give you a semi-simple element when the characteristic is not 2. And so anything that is F4 CR is automatically E6 CR and vice versa. But how about a non-example? Well, there's a really trivial one, which is if you give me a non-GCR connected subgroup, H, H is not ascending hereditary, so with an upwards arrow, because it turns out if you reread the definition from your notes that I'm sure you're taking, that a non-GCR subgroup H will be HCR itself. So that's what I mean by it being trivial, but of course I told you it was non-GCR, so of course it does not satisfy this ascending hereditary property. But it's a really cheap and not very nice non-example. But be careful what you wish for, because the real non-examples are really something I found in my end of my PhD thesis. So the kind of best way you'd think that maybe you're forced to stay completely reducible is if F was actually H irreducible. So never contained in a parabolic of H. You look inside G and you're like, well, surely there's not going to be some parabolic that comes along in G that gets it in and gets it in there in such a way that it doesn't live in a leg. Well, I thought that as well until I got towards the end of my PhD, found out that that's not the case. So if you look at all of the maximal subgroups and you look at their irreducible subgroups, it still turns out that lots of them can actually be non-GCR. Obviously, only in small enough characteristic, thanks to that theorem, but nonetheless. But there are quite a few, depending on your definition of quite a few. I haven't done that because I've then solved the representation theory problem that wins me the Fields Medal, I'm sure. G should be exceptional. We've seen if we're doing something for classical groups, we're just doing representational theory, and I don't think people know whatever the indecomposable nature of something would imply. And because it's for exceptional groups, it means giving an example for people that aren't interested in exceptional groups to the same level that I am, is a bit tricky. So I can tell you, for example, that you can take X to be of type P4, you can put it inside D8. This is via a spin representation. There are two such subgroups. And it turns out that one of them stays E8 irreducible even when P is 2, and the other one turns out to be non-E8 CR when P is 2. It's 2. This and X. X is D8 irreducible. D8 non-E8 CR. And then there's another one when P is equal to 7. A1 and A1, G2 and type 7. Okay. All right. So that's kind of upwards done in the exceptional groups, and in the classical groups, yeah, it's a representation theory question that is tricky for sure. So the work I want to talk about today is what about the downwards arrow? So I kind of claim it's even harder to have this go wrong. So, but again, people have already looked at it. And by people, it's our favorite triple again, VR. So if GH is a reductive pair, that means it means that E of H summand I believe G, and it really doesn't matter if that's not something you're happy with. And X in G is separable, which means your centralizer does not misbehave and grow any bigger than it should do. Yeah, think of it as some sort of reasonable restriction. Then X is GCR does indeed imply X is HCR. So if we write that to say then your H has this descending hereditary property, and there's a theorem due to Sebastian Herpel, PhD student of Gerhard Riller, which says that if P is pretty good for G, and I guess because they're German, they thought that pretty good was actually better than good, which is not true, but fine. I've already moaned about people renaming my things, so I'm not going to rename theirs. Better than good. Surprisingly. Not much stronger, in fact, but in any case, then every subgroup of G is separable. So again, you can get to a result which says if you're a reductive pair and P is big enough, then everybody is descending hereditary, which again is just a kind of reasonable sanity check that you're doing something right, that in characteristic 0, all of this is true because I don't have anything that's a non-GCR. So everything is true for 3. And so, for example, p equals 2 is never good. For exceptionals, it's also not good. Not good, pretty good, very good. Exceptionals. And so let me give you another one of my examples, which I do understand are probably testing the definition of example. So take P to be 2, and you can take a G2. I'll just put a load of symbols and then I'll explain. F4. Okay, so what I'm saying here, well, my G is F4, my characteristic is 2, so I don't have Purple's result. And then it turns out that if this was sort of x1 and this is x2, then I can sort of show you that you do need both parts of this theorem, because if this was H, H1 and H2, then GH1 is a reductive pair, but GH2 isn't. However, this X2, which I realise I'm not really telling you anything other than a chain of subgroup, actually, as it turns out, that does uniquely turn the subgroup out to conjugacy. And maybe I'm trying to give you an example of why it's complicated. So X1 and X2 is GCR, yet they're actually they're non-B4CR and non-C4CR. And they do all sorts of weird things because up until D4, they stay irreducible. So irreducible to here, become non-completely reducible in here, and then go back to being G completely reducible. So depending on your kind of tastes, I find that very interesting. Other people would say, why would you ever look at P equals 2 and F4 ever again? But yeah, I can't help it. You know, if I start collecting Pokemon cards or some other thing, I'm a completionist. So I very much would like to know all of these examples, and kind of give maybe a really best possible I'd like to know all of the subgroups H that are not descending hereditary, and I'd like to know all of the X's in them that are witnesses to them. And this is hard enough. So David Stewart will also be here later, so I'm say this. These should have been known to him in his thesis, but he claimed these two things were non-F4CR, and the thing is like hidden in 3 lines of his thesis that took Alistair, myself, and David Craven an entire conference of Warwick to understand where it had gone wrong. So that's not meant to be a diss at David. I can do that in the pub very easily. So a long-term collaborator of mine and would be very fine with that. But on this occasion, it really, it's unbelievably difficult because, I mean, yeah, there's just there's no indication that this thing that became B4, non-B4CR and non-C4CR should all of a sudden have enough conjugacy in F4 to put it back in a levy of this. It's in a B3 parabolic, actually, not that B3, just to be really confusing, of B4 and a C3 parabolic of C4, and then in F4, yeah, some kind of miracle happens. And my aim is, in 20-ish minutes, to sort of explain why that happens, and also to tell you a theorem of myself and my collaborators, which gets a bit closer to understanding the picture. Okay. Just that half of the whiteboard that doesn't appreciate the program. I owe an apology at this point because my abstract said it was joint work with Alistair Litterick and Martin Liebeck. That's because I copied the abstract from when I gave the talk in April. And between April and now, I had a conversation with Miko and we were able to do something I'll tell you about in a moment. And so he is definitely a co-author as well. And luckily he gets to go first anyway, due to the nature of the alphabet. So on and Litterick. Ways. Right, so let's take G now a simple algebraic group for simplicity. So if there is a witness, so if there is a connected subgroup, there exist connected subgroups X in H in G with X non-HCR yet GCR, and I still need to keep this reductive pair thing, talk about in a moment, then P is 2. Okay, so it is not true that that's just these two things put together. I did convince myself of that. Sure, we weren't publishing an empty statement by any means. So when I gave this talk the last 2 times, I was really annoyed about this condition, not because I think it wasn't necessary, but because I couldn't prove it was necessary. So I wanted to, I was wondering, and Alistair and Martin were wondering if we could just remove that. So that would be really nice. It says the only time you get this ludicrous behavior of being HCR and yet falling into a parabolic yet not in a levy is if P is 2. And everybody knows P equals 2 would be weird, so that's fine. So then I went to coffee with Miko whilst he was visiting Scott Harper in Birmingham. And as he likes to put it, he was shanghaied into the project because he told me an example when P equals 2. And I was like, well, that's all right. We were okay with that one. You know, usually someone says, oh, you need an example of something, here's P equals 2. But then we sat down for an hour and proved that you can't remove this for anything. So, well, for all P greater than 2, there exists, oh, that's actually one of those. You can put SLP into SLP cross SLP squared minus 1, which you can put into SLP squared minus 1. And you can do it in such a way that precisely you put SLP into SLP in the obvious way. And inside this one, you use the adjoint module for this, which in characteristic P is just a little tiny 2-step indecomposable with a trivial on the bottom. And then already in the literature, which was nice for Nico and I, because it saved us, we could have more coffee and less proving, George McNinch already has a paper, I think I mentioned him some time ago, which is, essentially tells you that the tensor product of those two things, which is what's putting this in value of H and G, goes back to being completely reduced. So it just falls out. And so you cannot just remove this reductive pair thing. However, you can remove it if, like me, you're obsessed with the exceptional groups. So Cheryl was telling us the history of many of her very successful collaborations. And on this occasion, Alistair messaged me. Barbara Baumeister was very surprised last week in Warwick that we do maths via WhatsApp. She'd obviously been looking over my shoulder at some point and noticing, she was like, you were doing maths via WhatsApp. I was like, I'll do maths via any messaging service. She was like, oh, is it not easier via email? I was like, no, I can see when Alistair's read the message and then I can start bothering him. So Alistair messaged me whilst he was a postdoc in Bochum or Bielefeld or both. I can't remember the exact thing, and said that he had been looking at lots of things and he had something to do with classical groups and when such a thing could happen. And we spoke about it for a bit, and I thought, well, of course, the exceptional groups must also be doable. And so we spoke and we sat down in Martin's office, and actually happened to be both of our PhD advisors. He's subsequently forgotten that. So he's constantly trying to get his name removed from the theorem. which I hope is more out of a he doesn't want to take credit where it's not due, and not because he hates the theorem. But you know, we'll never know. So the nice thing is I can make the theorem. So let's just say K T. I can remove the red bit if I make G exceptional. So G is an exceptional type. Then exists connected subgroup and H G with X on HCR, GCR, if and only if B is 2 and G2 is too small. So I can throw that away. And it's this bit where Miko is really feeling shanghaied, because I had a proof of this, but we had a proof of this. This was kind of my part, and I had kind of different choices at places, and some of them are much harder than others. And I was trying to make sure it was short and nice. So I asked them various representational theory questions that turned out to be quite difficult, and then in the end said, "Oh no, I don't need any of them." So I guess that is fair thing. Okay, so I think hopefully I've motivated why this is a nice result, but why I really like it is we can then go ahead and prove something else really quite quickly afterwards. So I gave you some examples of what sort of things are true about GCR subgroups. Another one that's true some of the time is what happens if you take a direct product of two completely reducible subgroups. But it turns out it's not always completely reducible. So again, another one of these ludicrous things that maybe you think should happen, some representation theory, or you think, wow, what a horrible thing to be true. So, and as we seem to be doing in this talk, we'll improve a result of BMR. So they had a theorem, they still do, BMR in 2008, which said if G is connected reductive, then the commuting product, I don't quite need direct, but commuting, what's a little finite center between friends, of two connected GCR subgroups. It's GCR if B is good. So that's not 2 for B, C, and D, and then not 2 or 3 for G2 up to E7, or 2, 3, and 5 for E8, but they already got rid of that. So commuting products of two connected GCR subgroups are GCR again. P is good, B is fine. E8. And much to my sort of amusement slightly, is that paper actually has a case-by-case proof in it. So Gerhard often likes to tell me how much he dislikes case-by-case proofs, and all of my papers involve some form of case-by-case proof. But even he had the result to one here. So much so, I'd actually, during my PhD, written it for myself. Then, yeah, should have checked the literature. Luckily, AI does that for you these days, so no problem. But we can do the sort of. I asked all of them at some various time why it should really be P good or not 5. And luckily now, basically for free, we get to say that the commuting theorem, right, holds if and only if G is of type, of which I mean the simple one, but if you take something semi-simple or even reductive with a torus, just make sure all of your types are in this list. A, G2, F4. So B equals 2 and 3 are not really a problem for G2 and F4. Or B, C, and D, as long as P is not 2. And so actually, as long as your P is not 2, this is a theorem which holds, which is nice. And in fact, things are too small in G2 and F4. And a kind of corollary, I guess really that's a corollary in this is a consequence, is that if you're interested in classifying non-GCR subgroups, yeah, it's one of my pastimes, then which are semi-simple, then thanks for this, you get to reduce to simple ones and then just finding their centralizers. So, and that is a big help, I can tell you. Very much semi-simple, then it suffices. Classify simple ones. And find they're connected. Centralized.
Yeah, don't exclude P equals 3 for the E series.
No, that's I wanted to be lazy, I could just say the commuting theorem holds as long as P isn't 2, but I know you can actually get these ones by epoch and P is 2. So how long do I have left? Some small number of minutes, but I'm
13,
sure
13 with questions.
nobody ever asks questions, so it's good. And it's lunch, right? So, okay, so let me give a proof. Again, historically, I think that's what you're meant to do. That's unwritten rules. So how do you prove this using this? Well, because I don't need to do anything in the classical case. BMR already told me that P is good, and that does this. So I only need to do something in the exceptional case, which is good for me, at least. Well, as is traditional, we use a lemma of BMR. So it's not like one before the proof of their theorem. In fact, in the paper, we will give a new shorter proof of this lemma, just to make that absolutely clear. But they have a nice lemma, which says the following. So if X is connected GCR, and you give me some subgroup Y inside the centralizer in G of X, which sort of makes sense. You want to tell me about X and Y, which commute. So Y wants to live in the centralizer of X. Then XY, by which I mean this commuting product, is GCR if and only if Y is CGX-CR. So stand back for a moment or two, and you realize that if you're going to find a failure for a commuting product of two GCR subgroups being GCR, then you're actually going to find me a witness for this failure. And now, well, we just proved you don't have such a witness. And the eagle-eyed amongst you will point out, well, you didn't get rid of F4 when P is 2. No, but my love interest of subgroup structure of exceptional algebraic groups mean with a bit more work, I can get rid of it. A bit more case-by-case work, just to make Gerhard happy. So let me just write, so with this lemma, suppose Y is GCR. I guess I should thank Alistair for moving me from the final conference to the first one. So I've been somewhat more careful with all of BMR in the audience. Whereas I can be more jokey without what happens. Very happy to say all the things I'm saying to their face, but I have to say it with a different tone.
I will be pointing them to the recording of this.
That's okay. I don't think I've signed any kind of release form, so it's fine. Right, so suppose Y is GCR, but XY is not. Or non-GCR. Then Y is non-CGX-CR, thanks to this if and only if statement by the lemma. And CGX search is therefore not downwards hereditary. So P equals 2, and G is not G2 by theorem 1. As I say, very system. Okay, so I've written down the proof, but I've told myself I can skip the F4P equals 2, 1. So, as always, I've written far more pages, and I think it's maybe the furthest I've got in the talk, but I guess maybe for a couple of minutes I should just tell you what goes into our proof of this. So I mentioned the classical one, which was Alistair's brainchild with co-characters and understanding quotients of unipolar radicals that don't even give you a group and take some tangent space rather than a Lie algebra, and I nod along, it's fine. So this one is entirely, so again, a talk about complete reducibility. Usually I'm always talking about non-abelian cohomology, because I told you I had to have something non-GCR, it has to live in a parabolic and not live in the levy. And that means that there will be some, you can push your subgroup into the levy, project in there, and you've got to see some cohomology on the unipolar radical. That's how you get some of these things. So to have one of these witnesses, you start off with it being non-HCR, so it's in some parabolic of H, but it's not in the levy. So somehow you find it. So I have X, it's non-HCR. So that implies that X is in some PH, UH, LH, and X, not conjugate to the subgroup of LH. And then miraculously, I end up with the property that if I ever put X inside a parabolic of G, it is always in. It's always conjugate to some levy. So PG is always consists of LG. And essentially, even though Q is non-abelian, and so we have to worry about non-abelian cohomology and pointed sets and all sorts of other things that are worse than you would hope, you can still look at this guy as a levy decomposition, and every parabolic of H, so co-character theory will give you a parabolic of G, and so you have to look at this. As I said, it's not a nice quotient in any way, but you can still act on it by things in the levy of H or G, and X lives in both of these, so you can project X, and there's a nice way to project it to the levy. And so you have to end up looking at what the fixed points of what we call X0 are on some quotient you think. And essentially you use a kind of short long exact sequence, a standard long exact sequence in cohomology, only in non-abelian cohomology it stops very quickly, and ask yourself questions about whether anything you have in here, so if you have no extra kind of fixed points in here, then you're good. There isn't any way that this non-HCR thing can magically become GCR. And even if you do have fixed points in here, it's not the end of the world, you're not dead. But you have to know that they actually lift to a fixed point genuinely on this. That will also mean your non-HCR thing stays non-GCR. So in the picture I raised some time ago, I had this ludicrous long sequence of subgroups and said it was an example. Well, it turns out in one of them, there is indeed one of these fixed points, so to speak, on this quotient, which doesn't lift, and that's the B4 one. And in the C4 one, it just so happens that the kind of cohomology just vanishes. The big parabolic has a trivial, has a fixed point, that just sits on top of the module that used to have cohomology and just says, no cohomology anymore, I've stopped that. And so that's kind of what we have to understand. And as I say, in the classical group setting, although it does work in general, it's an argument about this. And in the exceptional ones, we can kind of use the subgroup structure to see already, like from this lemma, actually gives us some restrictions about what subgroups could possibly give you weaknesses from this, and then kind of push it through. So I'll stop there. Thank you.
Do we have any questions for Adam? Don't prove him right. Go on.
I hate to disappoint your assumption of no questions, but I'd like to ask about this long ludicrous sequence, which I guess is a good opposite of short exact sequence of subgroups. So I mean, if you view F4 as the automorphism group of this Jordan algebra of 3x3 matrices, then G2 and D4, even in characteristic 2, sit very naturally as the automorphisms or permutabbilities of diagonal things. But I guess for this B4, it's not as natural. Is that somehow what makes it tick?
I would have said the B4 is kind of the most natural one. The C4 one only exists in characteristic 2,
Right.
by being an image of B4 under the exception morphism. But somehow, yeah, I mean, what sort of makes it tick weirdly, as I say, is that you just go all the way to B4 and find what's happening in the parabolic downstairs in the H, and then the little bit of extra unipotent radical you get by looking inside G just does exactly its worst kind of thing to force, or good, depending on whether you like or dislike CCR subgroups. But yeah, the G2 and the D4, at least in the B4 sequence, yeah, they're entirely just true over Z, sequence of subgroups. But yeah, I'm not really sure that I have a good reason. I also don't have a good reason for the thing I wrote where I sort of classified all of the failures of going upwards. They kind of had a pattern, but I could only prove it one by one that each one had this property. Whereas maybe actually if I maybe there is some inherent reason that at that particular prime it just has to break for some reason. But yeah, maybe if I looked at them as automorphism groups of algebras, it would show up very easily. But
The two D4s in those sequences are not the same subgroup. One is generated by long root subgroups and one generated by short root subgroups.
Yeah, the bottom chain is entirely at P equals 2.
Yeah, I think I'm more in the.
But the top chain is a characteristic 0 chain.
Yeah,
that goes to P. Exactly.
Why did you tell us the B3 and the D4? Was it just to narrow down which G2 was really like?
I just thought it was fun to keep writing out symbols.
It's
It's just how I think.
It does determine it uniquely though.
Yeah.
So yeah. Good. Okay. Well, were there any further questions? No. All right. Thank Adam again.